Do we have there is goon form?
Good form. I have never heard of that. I have no sweet form.
I have goon. I have active form.
From good?
I have no. When I have active form and goon.
Oh, the good tomato. You good the temper.
And then after the video, boom! I finish the work.
Shall we switch off that?
Yeah.
Wait. Oh yeah, Asuka. Right over. Switch on both eyes, right?
No. Only twice.
So we can use this diagnose to camera.
Yeah, sir.
Let's try, sir.
Okay, off the light one.
Hello, YouTube family.
Off the light one.
So how do you put the light? This light?
Yeah.
Off this, off the backlight.
I don't want to go ahead.
It's not that far.
No, sir, no. Let's go down.
Just go, man.
Let's go down. Sir, put higher setting. Higher setting. Good boy.
What are you doing?
So, modern is fine.
I think we discussed up to particle accelerators, right? Last time, and particle accelerators and particle detectors, isn't it? Right?
Yeah, Higgs boson.
Yeah.
Sir, I can't see you.
Yeah, okay, I'll play it. Next time we have to get a best time. Right.
So, we should call John Paul.
No, you don't need for you're not funny. That was like 10 years ago.
Sir, presentation.
Yeah, oh my
Go
god.
to slideshow.
I think Mark is in the car.
So again?
Can you? Yes.
So, you know where this is not right? That's it.
They are parked in
Yeah,
the
then
front.
you can get a
Oh, yeah,
Mark
then-
from this shop. It doesn't matter.
No, you don't need to buy, sir.
Can
Yeah.
Can you?
I don't know, sir.
Is it okay?
Yeah, sure.
This one, right?
Right.
This one, this one is,
Right.
Go you not?
Yeah.
I don't wish movement.
I think, I don't remember where it is. So I think it may be a little bit difficult to find. Maybe
I don't think I should.
4. Yeah. I think,
No, just go to the.
this one, yeah. This.
It's not money. So, money is rich.
No, sir, just 3 story house.
Let's start.
So after Plum's coding model and model quiz model, and these
No, it's extra. There's extra.
Is it? Honestly, an extra.
Yeah.
Is it?
Yeah.
And then standard model of particle physics. So, as I discussed earlier, using large shaded colliders, bubble chambers, and cloud chambers, they could determine
It's a slideshow.
some more. Yeah,
Okay,
it's a slideshow.
switch. So, we must slide on.
From beginning.
It's a
Right. Sugar, get up.
What's the sleeping?
Get up. Right. So this is mainly discussed under 3 main parts here. First is the fundamental, the matter particles. These are the matter particles, right? And bosons are just force, like force particles, force carriers. So yeah, boson, Higgs bosons.
Higgs boson.
Yeah. They are invented with the help of some favorite colliders. Then now we accept this model, right? I don't know what about after 100, 200 years this may be changed, right? Further, but now we are based on this basically, right?
So why is it gravity in the
Yeah,
standard?
gravity is not gravitons are not invented properly. Their characteristics are not measured like we can strong nuclear attractions like other electromagnetic. So these are the four fundamental forces, but graviton is not identified yet. Even the gravity is made of particles such that graviton, but it's not identified. Still, these experiments are done. So without these theoretical parts, we can't keep doing these papers, right? Answering papers. Right. First, we will be talking about the fundamental particles. Fundamental particles. Lepton is a fundamental particle, right? Is one of the fundamental particles.
So what are the fundamental particles?
Yeah, leptons and quarks. Right? Lepton and quarks mainly. We'll be talking about the others, baryons. What about baryons and mesons? They are made of quarks and a combination of antiquarks. I'll be discussing everything, but fundamental particles are known as leptons and quarks, right? So here these are leptons that can be split into three major generations. In the first generation, electron. All the experiments are conducted by many of these experiments are conducted by J.J. Thomson. Even he measured the ratio between the mass and the charge of the electron. The R American, he measured approximately, as I remember, it is minus 1.59 something. Yeah, Americans. Yeah, Americans experiment, hydrox experiment. So we discussed that derivation, right? Yeah. At the very beginning we discussed that. If you're interested, I will derive all those equations. Even in textbook also, they were derived, but the stocks, they're using the stocks law, that equation. They shown at once, if you are confused how it is coming there, then I will show the derivations regarding the viscose, right? It is in AS, right?
Yes.
Yeah, the combination of
Yes.
it's an electron. We know the relative charge is -1 and the absolute charge is -1.602 into 10 to the power minus 90 coulombs, like that. The mass is 9.11 approximately, right? These are estimations, minus 10 to the power 31 kilograms, like this. Then electron neutron, they determine another particle in the first generation. How do we differ this particle from electron? Yeah, this has no charge. Charge is zero, right? Likewise, there is a symmetricity. Then there is a fraction I can remember in your past paper. They filled 5 of them, and you are supposed to find the other one. Yes, the other one. Actually, it has been invented now, but you are asked rationally. You have reason why there must be another particle. Then you can see there is a symmetric, like a strategy. There is a symmetricity. Electron has its neutral particle. Electron, neutron, right? The sign is this one. The charge is 0. So this has 3 different lepton numbers. If it's a lepton, it means lepton number is present. If a lepton means lepton number is +1, right? Lepton number is +1. If it is not a lepton number is 0. Since this electron is a lepton, its lepton number is 1. You have to pay attention, right? Yeah, it is +1, right? Even this lepton number has been split into 3 different parts, but in your textbook it is not there, and in your papers also they never ask such questions. This is in your CGP. I extracted this script from the CGP. It's an additional fact, but no need to think about it too much, because this is an electron and this is muon and this is tau. It's according to 3 generations. The first generation is in electron, the second generation is in muon.
First generation.
So they were invented in 3 generations. They were invented in 3 different time seasons, like Yaswas and according to symmetricity, they help to invent the other particles. Yeah. Then the other one, the third one is tau. Tau, the charge is negative, right? Even muon's charge is negative. Muon's charge is negative. It's such that electron, but their masses are different. You can see that the tau's mass, this mass, and comparing tau neutrino, this mass is higher, right? Muons comparatively.
What's a neutrino?
Neutrino, it is a neutral particle. In all these three generations, they have three neutral particles. In electron neutrino, it is neutral. The charge is zero.
Why do we call it electron?
So
Why do we call it electron neutrino?
this is not mass. It's mass. Muon's mass comparing with this one, it is greater. Comparatively, this mass is greater. The relative mass, this gives the idea about relative mass. Tau neutrino, it is basically they are almost equal, right? So they won't ask too much questions like this, but you should have at least a general idea what happens to the mass is in your textbook. I'm sure that. So because in the bubble chamber, sometimes they'll be giving you two tracks like this. Then this is pion negative and pion positive. Right? This is a particle and antiparticle. It's on antiparticle, right? That's all. This is positive and this is negative. If it is antiparticle, it is pion bar, right? Then if the mass is higher, what happens with the curvature? It is under a magnetic field. We discussed in particle detectors. Charged particles are moving under magnetic field. If the mass is higher, what happens to the radius? Yeah, R equals mv over dq. Right. If the mass is higher, how do we derive this? F equals mv squared over r and F equals bq b. One of these velocities cancel out. Then when we subject the r becomes mv over dq. Without any derivation, you can use this equation directly. Right? This is the momentum of the particle. So since the mass is larger, the radius becomes larger. Right?
So what is Q?
Q is the charge of that particle. So in these bubble chambers or a cloud chamber, whatever the particle detector within that, then you have to make conclusions. There may be like they say there is a muon and electron, right? There is a muon and electron. So if you are aware of the mass difference between muon and electron, then you can get an idea who is the muon and who is the electron. Like they directly they won't ask what's the mass, who has the higher mass. But if you are not aware of that, you can't do it, right? Please, Masuda, get up. Masuda, get up. Electron, this is the mass. This mass, electron neutrino is pretty small, but muon is greater and tau is greater. Right? This mass is greater. So you should have at least this comparison. The idea of this idea, right? Muon is the mass of the muon is greater than the mass of the electron. Normally, the mass of the electron is 9.11009. This is 1.884 into 10 to the power minus 28. No need to keep that in your mind, right? I think in your scientific calculator is there under shall we check that for a minute, right? So that's the mu. I saw that it's there. Then it helps you, right? It helps you if you don't remember that. Even in you, and we have the same type.
So what the time?
So good. Yeah, in constant. constant, shift constant.
No, no. What's the simplest name?
Yeah, in mu, mass of mu. You have the idea of it, right? Mass of it.
And wait.
Yeah, they had the formula sheet, which they have attachment. Here we don't have it. Is there? It's 1.88 into 10 to the power minus 28.
Yes.
Right? Since the mass is higher, the radius must be higher. When it comes to a MCQ, I'll show you this type of MCQ question. You know exactly there is one of that particle is muon, the other one is electron. They have given that, but they didn't label who's muon, who stands for muon, who stands for electron. Right? So that's how this is connected with the other. If you know the mass of the muon is greater than the radius is greater, right? Because the relative charge is same as electron. This charge is same. Charge is not changed. It's changed and the same magnetic field.
If the charge is the tau neutrino, can they also give like that? Like the charge is different?
Yeah, tau neutrino is neutral. Tau neutrino is neutral. The neutrino is always neutral. And since these are leptons, their lepton number is what? The lepton number is always 1. The lepton number is always 1. I don't need to bother about these 3 different parts. It's enough to say exactly this lepton number is 1. This lepton number is 1. Right? It is enough. Just enough to keep in your mind. The lepton number, if it's a lepton particle, the lepton number is plus 1. If it's an anti-lepton, like anti-electron, right? We don't used to say anti-electron, but what are these antiparticles? Antiparticles are particles, those are having same characteristic except the charge. Mass, all the other characteristics are same as its own particle, but the charge is different. Even electron has its own antiparticle, which is anti-electron. We don't used to call that anti-electron, right? Normally it is symbolized using a bar, right? But for anti-electron, when we represent anti-electron, this is not the way normally we use this sign, positron. This is a positron. Not we don't used to call it anti-electron. Positron. What's going on? So there's no way to translate it into your dreams, right? So go ahead. What did you do today?
Grading.
Yeah,
Grading the whole day. Last day, sir?
Last day you say. Last day. So what's antimatter?
The antimatter is antiparticles are the particles those are having same characteristics except the charge. Charge is going to be switched. If it's an antiparticle, if it's anti-electron, the charge is positive. Charge is positive, then all the other characteristics, mass, those are the same way. But lepton number is switching to other. Lepton number is switching to what? The lepton number of this one is plus 1. The lepton number of anti-particle is negative. It's going to be switching to negative. So you should know this. It's not a big deal. You can rationally derive that. No need to recite this thing, right? No need to recite. I don't prefer reciting this thing. If it's a lepton, if the lepton is present, the lepton number is 1. If it's an antiparticle, it's all antiparticle, lepton number is negative. Is it out? These are the 3 generations. This is the first generation: electron, neutrino, neon, neutrino, tau, neutrino. These are the masses, right? If you use this calculator 991EX tells this, then there are these masses. If you forgot that, right? Especially in order to answer these MCQs properly, right? You should know the mass difference, who is heavier comparatively. Is there any doubt, right? So when we go through questions, we will find others. The next one.
Straight up and down.
Yeah. Mazukura, get up, please. Yeah. Right. I extracted directly this table from your textbook. These are quarks, other fundamental particles. These are fundamental particles means they can be split no more, right? So for now, as we know, these can be split no more, right? Because then many years back, in 500 BC, Democritus gave an idea about this atom, right? Still that term atom is used, but we could it was not a scientific proof, but it was an idea, right? So likewise,
if you cut a piece of paper or something to 1,000 pieces, there's a point where you can't cut it into like 2 or more, that becomes an atom. Right? That's his.
Yeah, if you can do that, right? And finally, you mean hold it infinite?
I think what's the philosopher's name?
Democritus. Yeah.
That's what he told, right? If you cut something, there's a point where you can't cut it, and then it becomes an atom.
Yeah. And the fundamental one, he called that atom. He didn't have any idea. It's made of electrons, protons. He didn't know anything. He didn't know anything at that moment, right? It was just like a statement by the philosopher. Then finally, when it is formed, then electrons, these subatomic particles, like electrons and alpha particles. Alpha particles are not atomic. Subatomic particles, the helium nucleus, right, is made of 2 protons and 2 neutrons. So at that moment, in the Rutherford's experiment, he used alpha particles. Alpha particles are fire. In the results, he used alpha particles. What are the major reasons for using alpha particles?
Why did it work?
So in Rutherford's alpha scattering experiment, why did he use alpha particles? What are some major reasons? What do you think?
The goal was so positive, right? So you can show
that experiment was conducted in order to uncover the structure of the atom, right? That was the major reason. So in order to do that, there must be a massive particle, to get an idea. And the other thing is, it should be positive. It should be charged particle, right? So alpha is a better one. So at that moment, they knew anything about alpha particles, the structure, and anything like that. Mass is gone, right? So they were aware of that. So those are the reasons. So the charge and the mass of it, right? Okay, then so even at that moment they didn't know the proton can be split further, right? But after the invention of these large hadron colliders, they could invent a series of these particles, and these are the fundamentals. As we know now, I don't know what happened when we go further after about 200 years, 300 years. Sometimes someone will detect that even this can be split. For now, right? Don't write it here, because these are the fundamentals according to this stage. Yeah, and then upper quarks and down quarks. So upper quarks, this is a relative charge, right? The relative charge of upper quark, upper quark, down quark in the same family meaning in the first generation. Osuga? Oh, Osuga? Get up! Otherwise I'm going to call you a grandmother. Get up. Right? Come back, come on. Yeah.
Move.
Take a shower and come back, please.
Shower.
Right. This is the relative charge is plus 2/3 and the relative charge of down quark is minus 1/3. Then you will be asked the composition of protons, neutrons, different particles. Right? So then this is strange in this second one, right? I used to keep this.
Strange.
Yeah. Then strange is another fundamental particle.
Nice name.
Yeah.
Why is it called up and down?
Because it's people up and
Yeah,
down.
actually this should be
Charm.
yeah, it should be sharp. It corresponding to this one, right? I used to keep that in my mind. Then you see, it's like it's cool, then but you have to stand, right? So because if you forget that, right? I mean, I think they know what's the reason they named these particles, right? Then at that moment, if there is a structural thing behind that, then they use that. Right? Then here is charm, and this is one is strange. Then, so who is the heavier one? Yeah, you can see these masses. When it goes down, what happens? The mass increases. You can see here. Fermions masses. These are the electrons, electron neutrino, neon neutrino, and tau neutrino. Even in the previous one, these are leptons. These are leptons in 3 different generations. Electron neutrino, the mass is lower comparatively. What is the other one? Neon neutrino, charge is 0 and the mass increases. And tau neutrino, mass is further. Okay, right. So what about these in first generation? Upper quarks. And respectively, electron's mass is greater. Right? But muon's one and tau's one are greater than electron comparatively. I showed that last time, right? So since they are in your calculator, then no need to keep. I think it's okay. It's better to know that, right? It's better to know that. Then because always, rather than checking the calculator, it's better to know this. Keep this structure in your mind, right? Then upper quarks, down quarks. They are in the same family, or they are in the first generation. So relative charges are like this. Then charm and strange. Charm, this is charm, and this is strange. Relative charge is 2/3. Relative charge of the strange is -1/3, right? Then when we move to the third generation, it is top and bottom, right? Upper is corresponding top, and this is bottom. This is third generation. This is right same way 2/3, and this is -1/3. Right. So you should know this, right? So the contribution for the baryon number from this is the same way 1/3, right? This is 1/3. The baryon number, the contribution for the baryon number in a textbook. I show you. Let me check. Could you please check this? Down bar. Please check it down. Down bar's bearing number, check that. Since this is not a lepton, the lepton numbers are zero. Because this is not a lepton.
Eximus.
No, down quarks, bearing number is 1/3. Right?
What charge?
No, bearing number. Then I asked Oscar, right?
It's
It's +1/3, right? It's +1/3 because the contribution to this protons and neutrons is 1/3.
So what?
Alright.
Very sleepy. Sleepy.
Is it?
Yeah, no, yeah.
So that's why you asked me to.
I think.
I can't check.
So we have class after this?
Yeah.
Do you have class after this?
Class?
After this?
Yeah, I have another.
Oh, great.
So,
7.
no, it's, yeah.
Are we eldest batch now? Are we eldest batch? Oh, is this happening? So what online?
Right. Okay. Hadrons, right? Hadrons is like the hadrons are like bonds, right? The holes in between in the nucleus, right? Like it affects on the baryons and mesons. So baryons and mesons are common like hadrons, then hadron like strong force. So let's see what are these variants. These are not fundamental particles, right? Hadrons are not fundamental particles because hadrons are governing baryons and mesons, and then especially they are in the nucleus, right? Especially they are in the nucleus, then hadrons can be split further. There are some examples, for baryons, like proton, neutrons, lambda naught. Well-known examples are protons and neutrons, right? Protons and neutrons. Those are baryons. Especially these hadrons are known as, they can be split into major parts. Hadrons are known as like the strong forces governing the nucleus.
Like covalent and ionic.
No. Those are chemical ones for the chemical solutions. These are not chemical, these are like fundamentals in the nucleus. Yeah. Right. So the baryons, even this can be divided into two major parts. You don't have too much thing here, right? And you have only these structures, then they will ask some certain type of questions. I will be discussing everything here. Baryons, its variant number is 1 since it is present. But meson's variant number is C. Variant number is denoted by B, upper B. Right?
So what's the variant number?
Variant number says something like, no, it's a contribution for these hadrons. Not the hadron, but the nucleus protons, proton is made of what? Proton is made of 2 upper quarks and 1 down quark. The contribution from upper quark is 1/3, and this is also 1/3. This is 1/3. That's how it's going to be. The proton's variant number is going to be +1. Baryon means baryon is made of 3 parts. The composition of baryon is made of 3 parts. The meson is quite different. It is made of quark and antiquark. That's why its baryon number is going to be C. So I'll show you that. For example, let's say it is UP bar. This is a meson. This is a baryon. The baryon's quark composition is it's made of 3 quarks. So when you answer these questions, you need this also. Please get up. Get up. Get up. Get up. Who's baby? Who's baby?
What is
Who's
baby?
baby?
Who's baby?
No, okay. It's a fundamental part.
Oh my God. I have a little heart attack because of your answer.
Let me say
Now here, these are hadrons are not fundamental particles. What are fundamental particles? We have only, as we know now, leptons and quarks, right? Leptons and quarks. And these hadrons are the strong
consist of
forces governing nucleus, right? They can be split into two major parts, further baryons and mesons, right? Baryons, the quark composition of them, the quark composition of baryons are made of, oh my God, here, look at this, please. Okay, shall I?
So you told him to shut up, and then you sleep, bro. Next one, last one. You sleep? Yes. Yes.
Please, just pay attention. Just after that, we can start answering papers because that's almost finished. That you need to form that. Then you can start answering. Today we can start answering. There's only one part left in I'll prepare the other slides for that. And many of these things are covered by this one, right? The particles is over, right? And here, look at this. The baryons, quark composition of baryons are made of three quarks. 3 quarks. That's what baryon. right? The variant number means the upper quark is a variant, the contribution from upper quark is 1/3. So the variant number complete is going to be 1, right? Variant number is going to be 1. Right? Then what about mesons? Mesons quark composition is quark and anti-quark. This is made of quark and anti-quark, right? Baryons are made of 3 quarks, and mesons are made of quark and anti-quark, right? This is made of 3 quarks, and baryons are made of quark and anti-quark. That's the composition. But you have to keep this in your mind. So quarks, basically its baryon number is let's say this 1/3. The anti-quark baryon number is -1/3. When we add them together, that's why the baryon number is going to be cancelled over and becomes 0. Right? Could you understand that why this baryon number of meson is going to be 0? Because it's made of quark and anti-quark. Quarks baryon number is 1/3, basically let's say it's down quark. Then down quark's baryon number is 1/3. Anti-down quark is -1/3. The contribution is in the other way, right? Because its charge is changed, right? It's regarding the hadrons, right? So then regarding hadrons means the contribution in the nucleus. That's why. Subtractions, these forces are in the nucleus, right? So then these are cancelled off. Then baryon number becomes 0. So you have to analyze these things, right? Okay, then these are the examples. Then we will go forward. Right. Again, baryons. I gave you a brief introduction about baryons. Baryons are hadrons made of 3 quarks, as I explained earlier, right? These are made of all these 3 quarks. These are 4 general. These are well-known baryons. Protons, neutrons. These are 2 baryons. You know, right? So then protons are made of 2 upper quarks and 1 down quark, right? Then look at this. The charge of upper quark is 2/3 plus 2/3 plus 2/3 minus 1/3. Charge of the down quark is minus 1/3. Add these 3 together, please. When we add these 3 together, yeah, it's going to be 1. It's going to be 1. These fractions, when you simplify together, it's going to be 1. Right? This is sugar. Right? You take a shower and come.
Don't poke my pole.
Indian bro.
On there was
Tidak kan ya? Sesawar dari tidak kan ya?
Oh.
Itu. It's 480.
What the?
480. Count is nothing and take it. It's fine. That's really very nice.
What? What?
Basically, if you fall into your again.
I asked him to have a walk and come back. It's okay. No, it's okay. Right. Right now, come back to the lesson. Yeah, we have waited. actually summary like.
Yes. Yes.
Tell me what are the fundamental particles?
Quarks and mesons.
Quarks and mesons? Quarks and leptons?
Receptions are like that.
Right. Here, quarks and leptons, I assigned it in the first 2 slides here because we should have. Also, again, look at these fundamental particles, right? Lepton. Are you okay? Okay. Yeah.
Yeah. Yeah.
This is okay now? Yeah.
Yes.
What?
420. Huh? 420. 420?
You wasted an hour.
Really?
Yeah, you wasted an hour.
I slept that much?
Yeah.
Wait, I slept that much?
Yeah. You slept.
I didn't feel that way.
Because Newton, Einstein's theory of
Jimmy's theory of
Because of my toughness, I was trying to acting like that.
super.
What?
Okay. Come back. Right? Leptons are fundamental particles, right? And other fundamental particles, you should be able to compare the mass of the electron, muon, tau. When we go through these 3 generations down, the mass increases. And even here, right? Even here in electron, neutrino, muon neutrino, in tau neutrino, it increases. Right? It increases. The mass increases gradually, right? But the electron's mass is greater than electron neutrino, muon neutrino, and tau neutrino, right? Then these are the quarks, upper quarks. These are in the first generation quarks, right? Even quarks are fundamental particles, right? What's the difference between quarks and leptons? Yeah, what's the difference between quarks and leptons? Even though these are fundamental particles, there is a major difference.
One up down,
Like electrons, leptons, under leptons you have electrons, neutrino, right? Like that, electron neutrino, muon neutrino, those in tau neutrino. They are basically in what? These are in nucleus, right? So they contribute to the nucleus. The electron, the leptons they contribute to the others, the outside of that. And certain energy levels, right? Okay, right. So that's the major difference, right? The quarks. These are the quarks and these are the masses, relative masses, right? So you are given mass in giga electron. Then there should be a giga electron was on c square. I think c square is. I started directly from your textbook. Right. Okay. Then this is the first generation and this is second generation. This is third generation. That's how mass increases. You should have a basic idea about this, right? Okay. Then the hadrons are like strong forces. Those are governing nucleus. That is split into 2 basic parts, like what? The 2 major parts of hadrons. The baryons and mesons. So what's the quark composition of barium?
Variance is 1.
What? Baryon's quark composition
3 quarks.
3.
is made of 3 quarks.
That
So
means-
last time we discussed quarks. Last time we discussed these quarks, right? So now baryons are made of 3 quarks. Baryons are made of 3 quarks.
That means what?
Yeah, it makes 1 because the contribution finally 1/3 becomes 1, right? So mesons are also made of
3.
quarks. But what is the quark composition?
Negative charge, anti-quark and quark.
Quark is made of antiquark and quark. What are these antiparticles? I didn't put this.
Antiparticles is the same particle, but the charge is changed.
Yeah, charge is changed.
Charge same mass of what?
Yeah, mass and others are preserved, but when the charge, not only the charge, but also it's a lepton. If it's a lepton, even the lepton now is going to be changed.
So
Right.
what is the electron now represent?
it represents the presence of that. If it is a lepton, it represents the presence of the lepton. If it is a baryon, since it's not a baryon, if it is a baryon, since it's not a lepton number of that baryon is 0. For example, proton is a baryon. Since there is no any lepton, it is not made of leptons, right? So the lepton number is 0. The lepton number of that is 0. The presence of or the contribution of leptons.
But what about the baryon number?
The baryon number represents the nucleus, the contribution of these quarks.
So baryon number is 3.
It's 1. It's 1 because down quarks, upper quarks, the contribution is 1/3.
Are you the overall charge?
Yeah. It's not a charge, right? It's like a force. As a contribution, it contributes. It measures the contribution to the force of the nucleus, right?
So we have calculation in this.
So
We have
no, the calculation means that we have to predict whether the reactions are possible or not. By comparing, if the reaction is possible, we have to check the charge conservation, mass conservation, relative mass conservation. That's basically checked in chemistry as well. And in a chemical equation, you know that, right? So rather than that, since we are talking about these fundamental particles, especially made in bubble chambers, when it's collided with another particle, then it forms more particles with energy. Because you know that sufficient energy is provided to make I'm really sorry for that. Then if we provide more sufficient enough energy to form new particles, it forms different particles, right? Like maybe pion, it will be given in the reaction. So then you have to check the consistency of the possibility of this reaction. So you have to check the charge conservation, whether the charge is conserved, whether the relative mass is conserved. In addition to that, you have to check the baryon number, whether the baryon number is conserved, and the lepton number is conserved, right? And the strangeness point. So we have to check those three in addition to relative mass and the charge. Right? So then we can say even in MCQs they ask these questions: who is the possible reaction? So we have to check that. So it is it's regarding this part, right? We have those kind of questions, not only in MCQs. Right? Okay. Is there any doubt regarding mesons and baryons? The quark composition of meson is a quark and antiquark, right? It's made of quark and antiquark. Quarks, baryon number is 1/3 and the antiquarks one is minus 1/3 because it is anti-quark, the antiparticle, so that's going to be cancelled off and the baryon number becomes 0. That's why the meson's baryon number is 0, right? Don't recite any of this, just try to understand logical pattern, right? Okay.
So after that, can you explain whatever?
Yeah, okay, then like proton, so this point 1/3, 1/3, 1/3, the contribution for the baryon number, it becomes 1.
3 quarks, all of them positive, then become 1. Antiquark is.
It's not a charge, right? It's a baryon number. It's a baryon number, right?
So upper god, so just SS.
Upper god.
Yeah, it's a omega minus. It's not plus
It means strange.
Ah.
Strange.
Yeah, it's strange. Strange. So what is charge of strange?
2 or 3.
Minus 2.
Minus 1/3.
Minus
This-
1/3.
This one. This is charge.
Yeah,
And this is strange. Minus 1/3. Minus 1/3, right? So
Yeah,
this is the
minus-
charge. If we define charge, minus 1/3, minus 1/3, minus 1/3. The charge becomes minus 1. The charge of that is minus 1. Charge of that is minus 1. And the baryon number, who is the baryon number? Baryon number is 1. Baryon number of this is 1, right?
Minus
So it's minus 1.
Yeah.
Baryon number is minus
No,
1.
no, it is 1. Since the baryon is 1. If it is anti-omega minus.
So that's minus 3 over 3.
No, it's a charge. It's a charge. It is the charge of this string. Charge of this.
Charge is minus 1.
So is the charge equal to the baryon number?
No. There is no.
So
In this table, they have given the everything. But even I think only important, we can check the answer. Yes, train is not given to the 60. But it is 61.
So what are the values of upper quotes and down quotes?
Upper box and down box, what are the
What are the charges of upper quote?
Yeah, upper box is about 2.
There, you wrote one over there.
Which one? This one.
Above that you wrote one over there.
It's not very enough. I wrote very enough, right? If you need to find the charge, the upper part is 2/3, this is 2/3, and this is -1/3. Finally, it becomes 1. 4 minus 1 is 3, 3 over 3 is 1. Right? Antiproton is U bar, D bar. Antiparticle. It's made of antiparticle.
So Mary number is
So, yeah. Varying number is negative. Is negative. Varying number of antiproton is negative.
Mary number means
Varying number is a contribution. That represents the contribution for the nucleus force.
Oh. So how to find the Mary number?
How to find the varying number is generally we should know the varying number of protons. Since it's a variant, varying number of proton is 1. You should have to know that, right? So I show how it's going to be formed. You see 1/3, 1/3, 1/3, right? Is it varying number or something?
Downloading your PDF.
What means
It's downloading the PDF. PDFs. Exactly, I'm a good voice.
Right, okay. Come back. So, the varying number of proton is 1, right? Varying number of proton is 1. When antiproton
-1.
it's -1. Right? So antiparticles, what is -1? Even the charge is negative. Charge is going to be changed. So you will be asked to distinguish right now similarities and differences between particles and antiparticles. So what are similarities and differences?
Antiparticles and particles.
Yeah. Differences, tell me differences.
Antiparticles and particles. Charge.
Charge is
different.
opposite. Yeah.
What's S then? That's also called.
It's strange.
Strange.
It's strange. It's another this is the is one of the in second generation.
That's another code.
Yeah.
That's our-
It's in the second generation. It's
Shut up and look at the box.
Neutron is made of upper core, 2 down cores, right? So that's how it's going to be neutron. Here, look at this. Neutron. Upper quark is 2/3, right? This is 2/3 plus 2/3, and down quark is -1/3 minus 1/3. So when we add all these three together, it's going to be 0. 2/3, then -1/3 is going to be 0.
Zero.
The charge is 0. But its change variant number is present. It's a variant because 1/3, 1/3, 1/3. It's 1. Variant number is 1. Variant number of neutron is 1.
How is it one?
The contribution from each is 1/3. So the variant number.
Each one.
Each part. Upper quarks and 2 down quarks.
But the
2 down quarks, the contribution from down quark is 1/3. For the variant number, this is 1/3. For the variant number, this is also 1/3. That's how it's going to be. The variant number is going to be 1/3.
So what's the charge of upper quark?
Charge of upper quark is plus 2. The charge is not equal to the variance numbers contribution. They don't misunderstand it.
So what's the contribution from you?
It's contribution of cell.
No. Look man, upper court.
Upper quark.
Upper
Yeah.
upper quark.
So he
makes
So Sir, we haven't seen you dark side. Of you having dark side the that is.
I didn't see that.
So do you get any, sir? Do you get any?
No.
No,
You never got angry at a child?
Sir, he's the most peaceful person I have ever met.
You never got angry at a child? You never got angry at a child?
Okay.
Not with child.
Really?
But you got mad at me, sir.
No.
That day for giving my maybe SRP book with money.
No, I got angry with that person because of your caps. It's like they all.
Bad boy.
Then,
Bad boys.
right,
Bad spirit.
please look at this number. Like lambda, right? This is lambda. It is in your syllabus. Here, look at this. So sometimes I have seen they give that, and normally they won't check for example memory like this composition, but basically you should know what protons and neutrons. Sometimes they are
So what is spin?
really.
Spin. Spin mark.
That means like how many rotations per second?
Yeah, it's been more than that. No. See, like you know that these numbers they have spin quantums. You have.
So what's the contribution of upper court?
No. Upper walk. Upper walk.
Yeah, upper court.
Not the right answer.
That's
Yeah. Contribution for what? Variant number.
You're very now.
Variant number is one part.
Always one. What about anti-cock?
Walk is minus one.
Minus one up there. Anti-upper court is minus one.
Empty about.
So S.
Yeah. Strain something.
What's contribution of down court?
1/3.
1/3?
Lambda.
It's
Lambda
very
zero
good.
is Lambda zero is right now.
Contribution of down third is also down cock.
Down clock is also 1/3. For the variant number, right?
Yeah, very nice. What about S?
Strain is 1/3.
1/3. Always 1/3 or everything?
Yeah, it's also.
Okay.
We will do some calculations.
That's
If you-
not-
yeah, interest, how is these variant numbers contribute to the new place, but it's not in our
Sunday,
calculation.
1/3.
Because it's not needed, right? So we will discuss first what are the things in our calculation, then after that we will go further. But I know that those are not given in the papers, yeah, they won't ask such questions.
Okay, next slide, sir.
Right, okay.
There is mechanism.
Classification of particles in mesons.
Regions are hadrons.
These are the mesons, right?
One
Mesons, so, also, what is the quark composition of meson? You can do it.
Just guess.
1/3.
One quark and
One
antiquark.
cock and one anti-cock.
Antiquark. It is a variant, it is a variant 3 quarks.
3 cocks.
3 quarks, not quark. Not quark.
Quark.
No, it's quark.
Oh, 3 cock.
That's quark. Okay.
I can't do anything.
This is the concept.
3 cock.
Right, okay. Look at this. This pion plus pion node, for example, this is made of U and U bar, right? U bar. Then how the variant number is going to be 0? This is minus 1/3. Variant number is minus 1/3.
1/3.
This is
We
1/3.
do,
That's how is the variant
zero.
number
We
becomes
do,
0. Yeah, it is window.
Yeah.
0, right? Then what is charge of this U bar and U? What is charge of upper quark? It is plus 2/3, and this is minus 2/3. The final is going to be 0.
0.
And the charge is going to be 0, final no.
So is that all 4 regions? That's all we need?
No, all the charges are not equal to 0.
No, I'm saying
But
is
variant
that-
numbers are 0.
Is that the concept? That's the only concept, right?
Oh, I didn't get that.
He's saying is that the only part we should cover with the reason.
Oh, yeah. Then sometimes in addition, they will be giving you different reasons. Those are not in your textbook. But like ion plus, they will be giving you sometimes they have given you, sometimes they have given you clues. It's made of this type of composition. Then you have to guess what are the combinations. Right? There may be sometimes combination for an arbitrary it's an imaginary one. Then you have to guess that.
So can you ask your question for mesons?
Okay.
Ask us a question for mesons.
Misses.
Yeah.
All right. Okay.
You ask me.
Let's see. Then let's say U S bar. D bar, right? S bar, D bar. So this is a meson, right? This is a meson. Right. This is a meson. Then the charge of this meson. The charge of this meson is 0. The charge of this meson is 0.
1/3.
What was
ये
it?
कुछ का
Sorry.
2/3
Yeah.
minus what is
minus 1/3.
it was is minus 1/3.
X is a meson. Is a meson.
The charge is always 0.
And no, it is not always 0. In this question, I am talking about this question, right? Let's imagine that there is a question you are asked. Then this meson is made of any of these two, right?
Yeah.
There are some combinations. You can see some combination. If it's a meson, there must be certain combinations. But they have given that the charge of this is 0. The charge of this meson is 0. The charge is 0. Next now, right? So you have to find what is the combination, correct combination. It can be US bar or it can be DS bar. Who is the correct one?
Or it can be
US bar is
OD, not
US.
US bar.
U.
How do you find combination?
No. S and D. S bar and D.
SA and D.
S bar and D.
S bar and D.
Yeah. How did you get it? How did you get it?
Since S bar is minus, so like
It's
S bar-
gauge.
S bar is plus 1/3.
Yeah. Then
and
charge is plus 1/3.
plus 1/3. And then D is also minus something. So boom.
The charge is 0. Then you took US bar. So what about U? U is plus 2/3 and S bar is plus 1/3. We find it becomes 1. The charge is 1. But I said that here the charge is 0. It's a neutral. Could you understand? Right? So they ask these type of questions. In some cases they have more than one combination, right? Sometimes they give these things and sometimes they different they ask the question. But anyway, generally you should be aware of this logic, right? Then I don't think exactly they won't focus, like if you don't remember what's the called composition of like chiral node, then they will not focus on that. They will be giving you some clues. Right? They will be giving you some clues, and regarding them you have to make them. So you know if it's a meson, definitely it's made of quark and anti-quark. That rule, that's sort of like a rule, and it is made of quark and anti-quark. So then they're carrying some experiments regarding vector quarks, but finally they realized that to make a vector quark, they had to make give more energy. Therefore, it is like impossible, or sometimes the lifetime is very small, and so here we don't have it right here.
Five big booms.
Yeah, chiral plus US bar, right? Chiral not DS bar.
D.
Right. Chiral plus, you have this thing, right? U bar or DD bar. Chiral not is U bar or DD bar.
DD.
Oh, otherwise attempt to mix it.
we don't need it.
Right. Because why is like in chemistry you know that, right? In benzene that bonds are like switching dynamically, right? So I think this one.
I don't. They know the dipole like it starts goes dipole. Yeah, dipole. Like dipole is a dipole.
No, I didn't remember those things. You used to draw resonance structures of chemical.
I mean like double shape like that.
No, those are the shapes of these orbitals. I mean,
Modern.
resonance structures. You draw resonance structures?
No.
You don't know?
Yeah.
You don't know.
This is already doing it.
It is like something like that, right?
I don't do only.
Is chiral node bar. Chiral node bar. When it comes to chiral node, it is chiral node is, look at this, chiral node is D S bar, right? Chiral node is D S bar. Look at this chiral node. Tell me, Yosuke, right? Tell me who is chiral node bar.
My friend.
Yeah.
Device.
Device. Good. So what is the charge of that?
Charge is
D. If you know the charge of this. It should be charged. Same as it should be charged. Charge is what?
Same.
Yeah. Charge is same. Because this charge is zero.
So this is zero.
Opposite of that is zero. Zero. Because it has no
One
charge.
and zero. Okay, so next slide. Next slide.
Right. Okay. Wait. What's the varying number of this? What's the varying number of this?
Zero.
Zero. Varying number of this?
Zero.
Zero.
Six is not.
In Mason's always zero.
Yeah, because it's made of quark and what's the letter number of that?
It's R plus 1. No, minus 1.
Oh
Is
my
there a
god.
letter?
No.
There's no letter.
So what's the letter now?
Is this a letter?
No, that's a quark. That's a quark.
Letters are, these are quarks.
Ah.
See,
So then they never related.
Yeah. They
Never related.
Yeah, never related means letter is absence here. Letter is absence here. These are in nucleus, right? So the letter number becomes zero, right? So you have to know this. No need to recite this thing, right? Okay.
Oh my god.
Four fundamental
Oh
forces.
my god, it's in Rolex. Oh my god, Rolex in
Crosswise.
Rolex in
Right. So, we will discuss hate. No.
This is a
And how do you author like 70 rupees?
I gave you two of them. So yes, strong.
Infinite water drinking of the
So strong. Strength.
Strong
So you mean strength?
nuclear
Strength.
force. Weak nuclear force.
Strength. The strength of a nuclear force.
This is so low.
Strength.
Not you.
I know. Don't go there.
You both are very adorable.
This one, right? These areas are governing the nucleus. So these are weak, weak forces. Right? Four fundamental forces in the universe. Strong nuclear. Then they are in different ways. They act on quarks and gluons. This column is not in your textbook, and this explains how they are interacted with these particles. There is strong nuclear forces. The range is very short and commonly found. They act on quarks and gluons on hadrons. Right? They act on hadrons. Nucleus. A carrier particle is known as gluon. This little g is not standing for, since it's not a stand for gravitational constant. It's 9.8. Electromagnetic. Charged particles.
So why are approximations accurate?
Approximate.
So are approximations accurate?
No, accurate means they are not accurate. They are not accurate. Accurate, what is the accuracy and the precision? Accuracy is the difference that represents difference between actual value and the observation. If there is a difference, the accuracy is low. If it is closer to that, accuracy is higher, but if it is absolutely, it should be the correct one. So here we use, for example, the speed of light, like 2.967 like that. Then then it is not used for the convenience of dealing with these calculations. We use 3 to 10 to the power 8. No, I would say that it doesn't make. It's not visibly. It's not a. The estimations are used to handle the question more conveniently and get a rough idea about the system. If you need more accuracy, we have to go for the accurate value, more accurate value. If you need more accuracy, for example, when you use pi in a calculation, right? If you need the accuracy of 2 fifth decimal in millimeters or somewhere, then you have to use that. So the actual value is up to that. Then pi, instead of pi, you can't use 22 over 7. If you need a higher accuracy, that can change the accuracy of the answer in the calculation. So it's up to the purpose. In some cases, in astronomical calculation, there are some calculations, their effect is changed by the 8 decimal or the 7 decimal. So in such case, you have to simplify up to its 7th or the 8th decimal. Otherwise, you won't be able to compare it, right? So that type of question we ask. So weak nuclear forces, generally it's overall fermions is like particles, right? The matter, matters, it affects matters generally. Like bosons, bosons. W plus, W minus. Sometimes they ask this theoretical parts. Right. Okay, then finally gravitational, the gravitons. So still, I think they did not find that it's like a theoretical idea. It's like a theoretical idea.
Infinite.
Yeah. Then you know after the Big Bang, these particles are scattered everywhere and they are created still because of the gravitational forces.
At the center of the Big Bang.
What?
When the Big Bang happened, and then galaxies.
I remember at the center.
The Big Bang happened right at the center. Let's say here.
Yeah.
And then
Yeah, what's it?
then the galaxies spread.
Yes, but studying amongst
Those galaxies have a gravitational force at the center of the Big Bang, right? Because they spread.
No, it's started with quarks. It's singular.
So why don't we send a drone to the Big Bang?
Still, there's
Fly Big Bang.
I think
Let's record the Big Bang. Let's send a drone.
it's not solved the problem. There is a confusion with the singularity.
Not actually.
If it starts with singularity, why is singularity? Why these are compressed onto different black holes, like different masses? For example, our check, our one is going to be, I don't remember the range. So they are different sizes. But if we start with the singularities, they must be in sync. It could not be explained yet, I think, when the person who is able to do that properly. They believe that it's a combination of this quantum physics and relativistic that can be, so we can try it, right? Okay. Next, still this is not invented, these are gravitons, right? It means even gravity, even though it's a field, it makes sense, is interacted with these matters, those are having masses, right? Those are having masses, and it's very small one because of that constant amount is due to the gravitons. It's due to gravitons. It's a kind of particle. It's a theoretical, right? It's a theoretical. Right. Okay. Then. As I discussed earlier, baryon number. The baryon is presence. Is three baryons are present, like protons, neutrons. Is one. The anti-one is negative. If no baryon is present, so it is zero. Otherwise, no, not only that, but also in meters, because quarks are having the opposite contribution, and they are cancelled off. Even at that moment, it's going to be zero, right? So they should be conserved, right? They should be conserved. Even the left-hand number should be conserved. If it's a left-hand, the left-hand is present, then +1. If it's an anti-particle of the left-hand, it's negative. If it's not a left-hand, it's zero. If it's a baryon, it's zero. If it's a meson, it's zero, right? Then strangeness is is quite different. Strangeness is quite different. If there is a strange particle, strangeness is negative one. Right? Look at this carefully.
So like,
Yeah, and it is should be checked. So they use that.
Explain using limits.
No, no.
The same.
Then I have checked that. No, there must be proof. So check. So question. I'll check. Then we'll check. Right? Then if there is no strangeness,
Last one.
yeah, strangeness is zero. If there is no strangeness is zero. If there is an anti-strange,
9 plus 1.
it's plus one.
Ah.
Isn't it other way? Isn't the other way?
other way, strange.
Yeah, isn't the other way strange?
It's talking about an ending.
So most of the times we won't check the strangeness because in the time given, then we don't have to check everything like paper. They will say. In some cases we have checked the strangeness as rare, right? Commonly we have checked charge and the relative mass and the bearing number and the vector. In some cases, rarely we have checked the strangeness as well. Right? Okay, we will do some corrections
So great.
regarding that. Yeah, first of all, we will see this.
Wow, so great.
Sigma.
Sigma.
So say it's some.
Yeah, the proton bearing number is 1 plus 1, right? So what is this now? Tell me,
Sigma.
lambda naught USD.
Minus
What is the bearing number?
Minus one.
What? Bearing number of lambda?
Zero.
Lambda naught is a barrier.
Zero.
Since it's a barrier, bearing number should be plus 1.
Oh yeah.
That's
You said 0 or something.
No, it's
plus 1.
Positron.
So sigma what was bearing number sigma and it's a positron.
Yeah, sigma.
Okay, so
Let's check this meson. Its bearing number is 0 because this is a meson. Neptune number is also 0. Strangeness is 0 because it has no any strange particle. Right?
strange.
You can look at this one right here. There is one strange particle.
Minus one.
Strangeness is minus 1. Because it has a strange particle. See the other way, it's working the other way. I'll check that. Right.
Any questions? I have a question.
I have a question.
part.
I have a question. What can we have right?
Oh,
What
is that
Yeah, there is another part, then I will be continuing that.
Yeah, go on.
Before that, we will start.
So let's go back.
My
Casino. Casino I club no casino. He was supposed to go.
I don't know. I just will let's go for
I don't know.
क्यों को ये how can you go work when you basketball every day?
He's tough for as well.
May go out at the young.
How we go? I mean,
Not out. Let's just go outside and
okay, it's a stay.
yeah, let's just